What we're going to do in 9.2 is still do confidence intervals, but they're going to be for a different type of thing, for a population mean. Anybody remember what the symbol for a population mean is? The average of the entire group.
Is it mu?
It is mu, exactly. Yeah. So this cursive U thing, that is the mean of the entire population. So you might see it referred to as a confidence interval for mu, the exact same thing. One thing that's different in 9.2 is that in 9.1, the variable was qualitative. Do you own a dog? Will you vote? Yes or no? Those are all types of variables where you describe what's going on in terms of proportions. 42% of people own a dog. In 9.2, we're going to be dealing with variables that are quantitative, like how many dogs do you own? And so we can think about taking the average. You can't even take an average of a qualitative variable. We're going to make a confidence interval for the average of a quantitative variable by doing the same idea, where we're going to take the point estimate, put it right in the middle. It's just one number that estimates mu, and we're going to add and subtract the margin of error. Pop quiz. Does anybody remember what the point estimate of P is? A population proportion. What symbol is the estimate of our population proportion? The Jeopardy music to play.
Is it p hat?
It is p hat. Fantastico. 9.1, we did a confidence interval with p hat right in the middle. So now we're going to be doing that same idea, but p hat is not going to be our point estimate of mu. Any idea? Another even harder question. The sample proportion estimates the population proportion. What is going to estimate the population mean? Another way I could have phrased that is, what number do you think is going to go right in the middle of our interval here?
Would it be mu hat?
That is a really reasonable response. It basically is mu hat. We just don't call it mu hat. We've used this symbol before. It's the sample mean is the way to describe it in words, x bar. So our confidence interval for a population mean is going to have x bar right in the middle. And then we're going to add and subtract, just like we did with a proportion. We're going to add and subtract the margin of error, which, just like with a proportion, comes from two numbers that get multiplied together. The one on the right is s over the square root of n. We used n in 9.1. That was the sample size. And we've used s before. Anybody remember what that is? It's something about the sample, I'll tell you that. And it's something that you can find if you have a quantitative variable, like height. You can find the average height, that would give you the sample mean, and then you can also find, how about this, it measures the variability of a quantitative variable.
Is it the standard deviation?
It is the standard deviation, faux show.
Okay, sweet.
So we're going to need that, the sample standard deviation. And the next piece is kind of the big deal different thing about a confidence interval for a population mean, which is this number right here. And with a proportion, that's a z-score. And with a mean, I'm just going to refer to it as a t-score. So this is a new thing. This is going to come from actually a whole different type of distribution. It doesn't come from a normal distribution. It comes from a distribution that's called a t-distribution. Sometimes you might see it referred to as a student's t-distribution. It's got a different name, a t-distribution, but it is similar to a normal distribution. It's still bell-shaped. A central t-distribution was what we use in this class, so it's still centered on 0, like a standard normal is. The main difference with a t-distribution is that which t-distribution, just like a normal distribution, if you have a different mean, you have a different normal distribution. A t-distribution is determined by a phrase called the degrees of freedom. I like to be efficient and abbreviate it as DF. So for a confidence interval for mu, that number, it comes from a t-distribution, but it's a t-distribution with the degrees of freedom has a really complicated, super difficult formula that you're going to need to pay a lot of attention to and spend many hours evaluating, which is you take the sample size, which is n, and you subtract the end. So you're going to have to do that kind of math. Hopefully we can do that. That's the last piece of a confidence interval for a mean. And the big deal is that now we have a whole new distribution here, a t-distribution. And let me just show you a quick example of finding this number here. Let's say we wanted to make a confidence interval for a mean. And we also need to know the level of confidence. Let's say we're going to make a 95% confidence interval for mu. And let's suppose our sample size happened to be 50. All I'm going to focus on right now is how the heck you get this number right here. T of alpha over 2, it's going to come from a t-distribution. I know you're all wondering, hey, which t-distribution is it? Well, here's our sample size. So our degrees of freedom is 50 minus 1, 49. For a 95% confidence interval for the mean, the t of alpha over 2, the t-score that we need to use, comes from a t-distribution with 49 degrees of freedom. That's the different thing. And what's similar is that because it's a 95% confidence interval, it's still the border of the middle 95%. We have 5% in total on the outsides. So just this one side here has half of that, 2.5%. So we're trying to find a percentile, and we're trying to find the 2.5th percentile of a t-distribution with 49 degrees of freedom. We have to find this. Here's a question. If this was a normal distribution, how do we find percentiles? I'll give you a hint. You had to use your calculator. Yeah, inverse norm. Lovely. This was a function we used to find percentiles with a normal distribution. Can we use inverse norm to find this number here that we need for our confidence interval for mu?
No.
No. Fantastic. No, we can't. Inverse norm finds us percentiles of a normal distribution. What function do you think is going to find us percentiles of a t-distribution?
Inverse t.
Inverse t. Fantastic. We need inverse t. If you have a TI-84 and you hit second in vars, the third thing down is inverse t. So you have a TI-83, you don't have this function. If you have a TI-83, you can program it. If you've never programmed anything, it's kind of fun. You could use a web page that lets you find percentiles from a t-distribution. But if you have a TI-84, you have inverse t. And the way that it works is the same as inverse norm. You have to tell it the area. For this example, what should our area be for trying to find this t-score for this specific confidence interval?
Would it be 0.025?
Yeah, exactly. Perfect. This is 0.025. We need to tell it what degrees of freedom we have. And that's all the information we need to give it. Because we're using 49 degrees of freedom, we want to find the 2.5th percentile of a t-distribution with 49 degrees of freedom. And when we do that, we get the t of alpha over 2, negative 2.01. And if you wanted to, you could use positive 2.01 because the math, it's the same thing as what happens with a confidence interval for a proportion. So that's really the big difference between finding confidence intervals for means and proportions. When you're working with means, you need to use a t-distribution. In 9.2, if you're doing a confidence interval for mu and you have this t-score instead, that depends on the level confidence. And if you get a different sample size, you get a different t-score. Normal distributions are involved when you're working with a proportion. T-distributions are involved when you're working with a mean. Let's make a confidence interval for a population mean. SARS? Sure. Let's do one about the SARS virus. This is number 33 in section 9.2. Our variable is we're measuring the incubation time of this virus, and it's in days. So mu is the average incubation period of everybody in our population. Let's presume it's everybody with SARS, and presumably in the world. So we don't know this, hard to know. So what do people do? They take a sample, and we're going to sample 81 patients. And then it says the mean incubation period of that sample was 4.6. So this 4.6 is the mean, but it's the mean of the sample. This is our X bar. And then it says with a standard deviation of 15.9 days. It's the sample standard deviation, which is S. It says based on this information, construct a 95% confidence interval for mu for the average incubation time of everyone. So our sample mean goes right in the middle, 4.6. Let's find the t of alpha over 2. The number that we want has the middle 95%. The bottom area here is 2.5%. So we need the 2.5th percentile of a t distribution, because our sample size is 81. Our n minus 1 is 81 minus 1. Which is 80, with 80 degrees of freedom. If you have your TI-84, you can just do inverse T, and then 80, and so we get our T value that we use. I tend to always use the positive equivalent because it doesn't actually matter. So when I do this in my calculator, I get negative 1.99. I'm gonna use positive 1.99. So 1.99 times the sample standard deviation, 15.9, divided by the square root of the sample size, 81. Don't remember the easiest way to find the sample standard deviation from raw data?
Would you plug it into your calculator?
Show. So stat, edit, put your data in L1, and then you go to stat, calc, 1var stats, get the mean and standard deviation if you just have the raw data. So anyway, we need to find the margin of error. I just do it all in one step. My margin of error of 3.52 if I rounded 2 decimal places. And notice that you only use the sample size minus 1 when you're doing the degrees of freedom. Oh, that's a pretty big margin of error. It's because we get this big standard deviation. So anyway, our confidence interval has the two numbers. One's going to come from subtracting and one's going to come from adding. So we're going to do 4.6 minus 3.52, 1.08, and 4.6 plus 3.52, 8.12. And that is our 95% confidence interval for the average incubation time of everybody that has SARS. You can see that we're not really that good at knowing exactly what it is. We know that it's in a range. We are 95% confident. We're pretty sure that the average incubation time for all SARS patients is between those two things. Is there a unit on these? Yeah, these are days. Perfect. Yep. And 8.12 days. So again, the confidence interval just gives you a little bit more information than the point estimate does. Our point estimate of 4.6 is incomplete. The confidence interval includes the idea of how much were we able to pin down this unknown parameter. Here's a question that comes up in the homework. Is it possible that mu is 9?
It
is.
Yeah, it's
Yes.
a slight chance, but
Yeah. Yes. It's definitely possible. Just one thing that you don't want to say is that there's a 95% chance mu is in here, because either it is or it isn't. This 95% is the chance that the whole process will be accurate. Do we ever actually know whether mu is in here in our interval or not?
No.
Lovely. Another philosophical thing about statistics. You never know whether you're right or not. So we can say statements like, we're 95% confident. We're pretty sure that we're right. We recognize that we could be wrong. What was the margin of error for this confidence interval?
3.52.
Yeah, exactly. 3.52 days. Point estimate was 4.56. Great. I'm not going to discuss anything else. I'm happy to answer any other questions about anything. Otherwise, I think you pretty much have what you need for the homework. If you want another example of doing this, you can watch one of my videos. Thank y'all for stopping by, and hope everything's going well out there.
thank you.
Yeah, of course. Definitely.
Yeah,
You can also email questions.